Friends, welcome to this channel Dr.ARM's Chemistry. Last time we were discussing the organometallic chemistry and we have seen various points involved in this topic. And today we are going to see the next point of this organometallic chemistry, that is bonding in organometallic compounds. Bonding in organometallic compounds. This is important because many reactions or every reaction shows its or determines its future, whether it will undergo reaction, means whether it is stable or whether it is it is unstable. Means these things are determined by understanding the nature of bonding. So first of all, we come to know that the nature of bonding which is concerned to the organometallic compounds is the metal carbon bond. So here the most important thing is that the metal carbon bond, and if we consider the organic moiety like CH3, then the methyl group provides the carbon and this carbon is bonded to metal, and the reactions involved are concerned to this molecule M metal with CH3 bond are dependent on the stability of this bond. If this bond is weak, then this molecule is reactive and it will undergo any variety of substitution reactions. If this bond is stronger, then it will not be broken easily. So it will require more or stronger conditions such as providing energy of activation, that is high temperature, or any other catalyst, etc. And then only that strong bond can be broken or weakened, and then only this molecule will undergo any substitution reaction. So we have to study this. So this is a sigma bond, and generally the sigma bond is stronger. This is stronger, sigma bond is stronger, and in that case the molecule becomes stable, and it means it is not highly stable, it may be stable to some extent, and after action of certain reagent it will undergo the desired reaction. So using this example, we can say that the sigma type of bond takes place using the orbitals of both metal and this carbon. So the metal orbitals and these carbon orbitals are involved in the interaction, and which will result in the formation of this metal carbon bond. These bonds are similar to those with when the metal is transition metal or when the metal is alkaline earth metal, means main group metal. So this metal can be a main group metal or this can be transition metal. So depending upon the nature of metal, the fate of this bond will be shown or it will be observed. So this bond is also relatively stable in case of main group metals. In case of, for example, if we see SN CH3,4, that is tetramethyltene. So We have seen already variety of examples in such case. Now we will try to understand. So this sigma bond in organometallics or metal organics, in metal organics or organometallics. So this is usually unstable. It is usually unstable. And if we see the examples, such as some examples or simple examples, that in that simple compounds, mostly the product, that is metal organics means organometallic compound, is stable. But in some cases, the metal or organometallic compound is unstable. So if we take the examples of the TiCH34, then Sb is antimony CH3 and tungsten CH36, then it is found that these species are stable, and that is why these can be characterized, means we can determine their characteristics, and for this purpose the this compound should be stable at least to some conditions. Then and then only the characterization is possible. But these compounds are stable up to certain temperature condition, and if we see their characteristics, that it shows that these compounds are stable up to certain temperature range. But if they are brought to higher temperature conditions, then they are decomposed slowly with rise in temperature, and they after exposing to higher temperature, it further undergoes the violent reactions or violent observations are seen. So in the presence of other ligands, if we see the example such as TiCH34, here you will find that the 4 methyl groups are bonded to titanium metal iron, and this compound starts decompose at up to -70 degrees centigrade, means about -70 degrees centigrade, means it is stable up to -70 degrees centigrade. But as there is rising temperature, the compound will show decomposition slowly, and this rate of decomposition will go on increasing with rising temperature. If we take another example, that is TiCH3Cl2, so the difference you will find that 2 of these methyl groups are replaced by Cl2. 2 of these methyl groups are replaced by Cl2. So that is why we got this TiCH3 twice Cl2. Here if we find that this CH3 group, methyl group is electron donating. It has electron donating ability. So in the TiC bond, this will supply electrons to titanium. And here in this case, you will find that there are 2 methyl groups attached to this titanium, but 2 Cl are also attached to this titanium. So these 2 Cl are having electron attracting power, and that is why the bond between this titanium and Cl is becoming relatively stronger, and that is why it becomes more stable, means it will decompose relatively above this minus 70 degrees centigrade, and it shows that it can be prepared. Means it is stable above or at minus 20 degrees centigrade. Means you will find that minus 70 is much cooler condition than this minus 20. So at this higher temperature also means it can be easily prepared, but this will be prepared below minus 70 degrees centigrade. Then again, if we see another example, that is, if the methyl groups are replaced by amines, that is say TiCH3 twice, NH2 twice. Amines is NH3 twice, that is amines. So here this nitrogen is again more electronegative, means it has a lone pair of electron, and that is electron donor. So that is why it is again more stable, and this can be prepared at still higher conditions, and so it can be stable at even 0 degrees centigrade, at 0 degrees centigrade. So you can compare these ligands. Here you will find that there are all methyl groups surrounding the titanium. So methyl groups are electron donor, that is why it is stable up to minus 70 degrees centigrade. But in this case you will find that two of the methyl groups are replaced by Cl2, and this chlorine is more electronegative, and it has electron attracting power, strong electron attracting power. And this nitrogen has also it is also more electronegative, and it has also electron attracting power. Means it has formed the ligand, means this titanium nitrogen bond, and here it has used the lone pair for bonding with titanium. But this bond is stable till this lone pair is here used between titanium and nitrogen. But if this is compared to titanium, this nitrogen is also more electronegative. So this lone pair is shifting towards this nitrogen, and that is why the titanium carbon bonds are stronger. Here also titanium carbon bonds are stronger because chlorine is more electron attracting group, and that is why compared to Cl, this nitrogen, this amine are more stable. They can be even prepared at 0 degrees centigrade. Instead of methyl group, if we use other higher alkenes, if we replace these groups, these four, with higher alkenes, then these are more unstable, or we can say less stable. So such are less stable. Generally we know that the alkanes, higher alkanes are more unstable, means they are less stable, whereas lower alkanes are relatively more stable. So if we replace these alkyls, means these ligands are further replaced by aromatic ligands, then you will find that these are further more stable. So aromatic organometallic compounds are more stable. Then we will see examination of the factors affecting affecting the metal carbon bond stability. Metal carbon bond stability. So when we observe this, we will find that first, that is, the metal carbon bond is relatively weak. We have seen it already just now, and there is little quantitative data available for this purpose. But we note that the thermal instability and force constants are fairly low for this metal carbon stretching vibrations, so which are responsible for its reactivity. Then it is also observed that organic products which are obtained after metal carbon cleavage, that is metal carbon cleavage. So after cleavage, this we give this metal free radical plus this organic portion. So we will see this Cr4 or Cr3. So we will get metal free radical plus this carbon free radical. So that will be more reactive than this. So cleavage of this metal carbon bond will result in the formation of such type of products. So these products are highly reactive. And this cleavage, they will be reacting rapidly with these are reacting rapidly with solvent, either solvent, or they will react with each other. Either they will react with each other or they will react with the solvent, and they will give the new products. Whereas the cleavage of metal ligand bond, this will give us the product, like means, for example, if we take this is the generalizing, if we take the example of MOH2 bond, so that will be undergoing cleavage to give us the metal plus OH2. This is not 0, this is OH2 means H2. Or if it is metal chlorine bond, then after cleavage it will give this metal plus Cl minus. Metal plus Cl minus. So these are more stable. And that is why the cleavage is more favorable. This cleavage is more favorable. This forward reaction is more favorable because the products of cleavage are more stable. Then the third case of this stability is that the bonds formed in this cleavage of organic products are relatively stronger. The bonds formed by the cleavage of organic cleavage products, bonds in cleavage of bonds formed on cleavage products are strong. For example, the bonds are say carbon bonds. Means when we see the methyl free radical is formed, it will undergo reaction with each other to give methyl means ethane. When two free radicals of methyl are combining with each other, it will give ethane. Similarly, ethyl free radicals will combine with each other to give the butane, etc. So in that case, you will form the formation of carbon-carbon bond. Similarly, carbon-oxygen bond, carbon-nitrogen bond, carbon-halogen bonds. So depending upon the system, the products are obtained like this. Thus, we have seen the reaction types. So if we see the model reaction, the model reaction. The model reaction can be shown as 2MCH3. If we take the example of this methyl, it means the molecule is not only like this MCH3. It depends upon the oxidation state of the metal. Means it can be, if we take the example of titanium, there are 4 methyl groups, but we are generalized here as M, and we are concerned with the metal carbon bond. So that is we have considered here as a part of that. After cleavage of this bond, so after cleavage of this bond, we get the product of the after cleavage, that is CH3, and M, that is metal. So these are the products. So if we say this is the reaction 1, so here the forward reaction is exothermic when we get this product. The forward reaction is exothermic, means the bond fission, that is bond breaking, is very easy process, and dynamically this is preferred. Further, any equilibrium involving in the cleavage state, first cleavage state, we observe that thus this methyl carbon of NCH3 will form the product like this. It will give methyl free radical plus this metal free radical plus methyl free radical. So this is say second reaction. So here if this reaction is driven to the right, the reaction will be driven to right where the free radicals are formed, and that will be removed. Means if we try to remove these products from the reaction, that is if we remove the methyl group, methyl free radical from the reaction products, then this reaction is more directed in forward direction. So that is favorable in forward direction, and that is why reaction rate of reaction will go on increasing. However, even if the compounds are thermodynamically unstable with respect to decomposition products, their lifetime depends, means how long they will keep their existence, or that depends on the rate of reaction. Means if the rate of reaction is faster, then the products are relatively having more life. Means they can be removed easily and they can be used in the reactions. So that is called their kinetic stability. So this is called their kinetic stability. So their lifetime may range from very short to the indefinite. This may range from the lifetime may range from very short or extremely short to indefinite. Means it will remain nearly stagnant. Then if we see the main factors, main factors affecting kinetic stability. Main factors affecting kinetic stability is the size of input energy, size of energy input, and that is called energy of activation. So this will determine the kinetic stability, means whether it is stable or reactive. So the energy of activation is provided to the molecule so that the bond, that is metal carbon bond, will be easily broken and it will undergo variety of reactions. So as we have seen earlier in first and second reaction, so that activation energy is an important factor. Such an input energy, so that will be used for bond breaking or bond weakening. So formation of an intermediate is possible as a result of this, and population of antibonding orbitals is also increasing when the energy input is more. The required energy of activation is large. When this is large, then the molecule is more stable. So that is, the compound is stable indefinitely. Compound is most stable, or stable is indefinitely more stable. Even if we provide the necessary decomposition, or even if we provide more energy, and the overall decomposition reaction is favorable, even though the compound will be stable. Free energy changes are also favorable for this reaction, then also the compound will be more stable. Similarly, similar comments can be applied to the stability to other reactions such as oxidation or hydrolysis. So such things are also applicable to other types of reactions, that is oxidation or reduction. So we will stop our discussion. See you next time. So please, if not subscribed, you please subscribe to this channel and also press the like button if you think it better for your benefit.